So the last time we started chapter 27 about circuits, we started with a simple circuit like this with a battery and a resistor. And the battery, we consider normal battery, not ideal. So it has this internal resistance in it. And there is a terminal voltage also we call VAB. The EMF of the battery is E. The difference between EMF of the battery and terminal voltage comes from this equation because of the internal resistance of the battery. And VAB, terminal voltage, is usually EMF minus R times I, where I is the current going through the battery. If the current is zero, the VAB equals to terminal voltage is equal to the EMF of the battery. But when there is some current in the battery, these two are different. So for ideal battery, R is zero, means there's no internal resistance. Therefore, terminal voltage and EMF of the battery are the same. So this is for ideal battery. We usually consider ideal battery because we're just talking about the basic principles here. And this figure shows how potential changes when you go through the battery from A back to A, going counterclockwise. Here, the potential is VA, and then if you cross the battery, it goes up to EMF of the battery, and then go over the internal resistance that reduces the potential by I times R. I is the current. I use capital I. The book uses lowercase I. So here we have VB, and all the way from here to here, VB is constant because these connecting wires are conducting, ideal conductors. And then passing through the resistor, the potential drops by I times capital R, and then we are back to potential of A. All right, so this is just looking at the simple circuit. And then we talked about the resistors in series and parallel. The resistors in series are like this when they have to have the same current. The current is continuous here. Any current that passes through R1 has to pass through R2 and R3. Otherwise, there will be accumulation of charges in between, and you know that it's a large charge and it will be explosive. So the current is usually continuous and can branch like this, can branch into a few branches, but when there is no branching, the current has to be the same. So by definition, the resistors in series have the same current, but the voltage from A to B breaks into A to X, X to Y, and Y to B. So it will be sum of the voltage across the resistors, and we can replace this combination by one resistor that basically has the same current for the same voltage AB, and that is called R equivalent. And we figured that equivalent resistance will be sum of the resistances in this case. And if you have resistors in parallel, which is when they have the exact same potential, because one side of the resistors are all connected by conducting wires, the other side are also connected by conducting wires, and therefore all of one side are at the same potential, all the other side at the same potential, therefore potential across each one of them is the same. But the current, as I mentioned, branches into three here. So this current total becomes sum of the currents, but the potentials are the same. If you replace this combination by one resistor that has the same current for the same potential difference, that's called R equivalent, and it comes from this rule that is like inverse law rule, that R equivalence inverse is equal to sum of the inverses are the resistances. Any questions so far? All right, we did that, and then we said that there are some cases when we want to solve a circuit, it means that we have a circuit, we want to find the resistance, we have several resistors, we want to find the current and potential difference across each resistance. And when there's only one battery and a bunch of resistors, usually you can reduce it to only one equivalent resistance and the battery. First, like for these two, for example, 6 and 3 are in parallel, and you can calculate the equivalent resistance and becomes 2 ohm. And you replace the 2 by this 2 ohm battery, and then these two now in series, you replace them by a equivalent battery. Now we have only one battery and one resistor, and we can calculate the current through it. And then we go back step by step, and we carry information on until we find all the currents and potential differences. For example, when we go from here to here, we say that the current is the same, and therefore now we know currents in these two. And now when we know the currents, we can find the potential differences. And then when we go from here to here, because these two were in parallel and replaced by this one, the potential difference across this is the same as the potential difference across these two. Now we know the potential difference and the currents of all the resistors. So this is basically solving the circuit. And now also we talked about the energy conservation or balance of power. We said that this battery puts out this much power, and the resistors, each one consumes or dissipates some power. And you see that sum of these three becomes exactly that. So when a circuit is completely solved and show the energy, conservation of energy holds for any circuit. If the conservation of energy doesn't hold, means that something is wrong. All right, so we can, this is a check, and you can go back and see what is wrong with the solutions. All right, so these are a single loop circuit, means the circuits that can be reducible to one single loop. But there are some multiple loop circuits that are not reducible to a single loop. An example is this. You see there are 3 resistors here and 2 batteries. And you cannot reduce this circuit because none of the 3 resistors are neither in parallel nor in series. And also the batteries are neither in parallel nor in series. Batteries can be in parallel or series, but in this case, they're not. So you cannot reduce this circuit to any simpler form, okay? So the question is, what do we do in this kind of situation? So it is not a simple matter of writing V equals to Ri for any one of the batteries or the combination of resistors. It's not that easy. And the situation is very different when you change the resistances and the EMF of the batteries. So in these kind of situations, when the Ohm's law doesn't directly apply, of course it applies for if you write the potential difference across this R2 and the current in R2, you can say V equals to Ri for that resistor, but we don't know what is the potential difference between here and here. We know what it is between this point and this point, which is the EMF of this battery and so forth, but we don't know the potential difference across each battery, each resistor. And therefore, we cannot know what current goes through them. So in these kind of situations, we have to go back to more fundamental laws of nature. For example, we can use conservation laws like charge doesn't get destroyed or created. And also, if there's electric field that drives the current here, if you go around one loop, because electric field is conservative, some of all the potential differences are come up to be 0. So one of the conservation laws is, as I said, conservation of charge, which turns into a rule that's called Junction Rule. And another is conservation of energy, which is called loop rule, or sum of potentials equal to 0. For example, if you take a charge here and move it along the wire in one loop, then you see that the potential gain, electric potential energy gain and loss will be balancing to 0, because you go back to the same place. There's no change in potential energy at that point. That's why this is called conservation of energy. And conservation of charge is whatever charge comes here to this junction should go somewhere, either here or here. All right, so the junction rule, therefore, states that at any junction, the sum of all the currents coming into a junction should match the total current going out of the junction. Or in mathematical form, we write sum of the currents in is equal to sum of the currents out of the junction. So for example, if you consider this one, say if there's a current coming here and there's currents going out in here and here, then this current should be equal to sum of these two, and so forth. And the loop rule says that around any closed loop, the total potential differences should be 0. And we write as this: sum of delta V equal to 0 for any closed loop. Means that, for example, you can take this closed loop, you can take this closed loop, or you can take the larger closed loop, or it doesn't matter which way you go. If you traverse the circuit in many different ways and come back to the same spot, then some of the potential differences that you encounter should add up to 0. So this comes originally from conservation of energy. This comes from conservation of charge. All right, any questions so far? All right, now these are, by the way, called Keshov rules. These are the summary, junction rule and loop rule, and then we have some sign conventions for loop rule. For the junction rule, it is pretty obvious. The currents coming in and going out should balance. But here we say sum of the delta V equal to 0. Of course, some of these potential differences are positive, some of them are negative when you go through a loop, and they add up to 0. And so we have to have a clear convention about when we consider a potential difference across a device in the circuit. We consider positive, or sometimes we call, and when we call them negative. For example, when we pass through the batteries for EMF, we said that if you travel in the direction from negative side of the battery to positive side of the battery, it means that the battery is here, this side is negative, this side is positive. You go this way through the loop, you're going from negative side of the battery to positive side, you consider plus E, or plus EMF of the battery, or voltage of the battery, for change of the potential, because this side is higher than that side. So when you go in this direction, you increase the potential by E. And on the other hand, if you go in the opposite direction, means that going from positive side to the negative side, the delta V for battery will be negative EMF of the battery. Right? Does it make sense? It's very intuitive. You go down in potential, you get negative change of potential. You go up, you get positive change of potential. And then for resistors, if you pass a resistor, if you travel, if you know the direction of the current through the resistor. If you go against the current, because the current goes from positive side to negative side, or from higher potential to lower potential, if you go against the current, you're increasing the potential. So you consider the potential difference of positive I times R. If I is going through the resistor and its resistance is R. And if you go in the opposite direction, means going that in the direction of current, you consider negative IR. Because you're going in the direction of current, the current goes in the direction of lower potential, so you're losing potential. All right. So these are very intuitive, but we need to be careful when we write down these conservation laws, especially loop rule. And it depends on which direction we are going around the loop. For example, if you're going along the loop this way, for this battery, we're going from positive to negative. But if you go along this loop in the clockwise direction, for this battery, we're going from negative to positive, right? So it depends on which direction you're moving through the loop and passing through the battery or resistor. We need to be careful when to put positive or negative for potential differences. All right, any questions so far? All right. So here is the same circuit basically. Now we assume that the batteries have EMFs E1, 18 volts, E2, 12 volts, and R1, this resistor is 4 ohm, this resistor R2 is 6 ohm, and this one is 12 ohm. Find the magnitude and direction of the current in each resistor. We want to know what current goes through each one of these and in which direction. All right, so we said that the potential differences when you want to write Keshov rule depends on the direction of current, and we don't know the direction of current. What do we do? At the beginning, we are not sure of the current directions, all right? So we start with guessing the current directions and assign a name to the magnitude of each current. So this is complete guess. It can be wrong. It doesn't matter. Then we apply the Keshov rule and form a system of equations and solve for the unknown currents. It is quite all right to guess the directions wrong. Whenever you put the wrong direction for a current in one branch of the circuit, the answer for that current comes out as negative. That is how you know that the actual direction is opposite of what you guessed. So let's just put random directions for the current and name each one. Let's say I1 is this way, I3 is downward, I2 is upward. So you see, this I3 obviously is wrong, but the other two could be wrong, could be correct. We don't know. But it doesn't matter. You just take any direction that you want and then write the equations according to those directions and don't change it. Here, the direction of I3 has been chosen wrong intentionally. The other two might or might not be wrong. Now we can choose a junction and apply the junction rule. In the figure, there are two actual junctions, B and D. You see here, there are 3 branches connecting to each other. Here also 3 branches, 3 wires connected at junction. The 2 points A and C, you see this point and this point, might be considered as junctions, but they are only trivial because just the current that comes here goes this way or vice versa. This I2 comes here and goes this way. So it doesn't give us much of an information. So, but what can we say about junction B? If you apply junction rule for B, we say that this current I2 comes into the junction and I3 goes out and I1 goes out as well, right? Because here the current is continuous. So I1 goes this way, from B goes away from B, I3 goes away from B, I2 comes into the B. So therefore, we can say I2 is equal to I1 plus I3. Okay, does it make sense? All right, so you see, we don't know if these directions are correct, but we write the equations according to these currents as if they are correct. All right, so we say I2 comes in, I1 and I3 go out. So we have to have I2 equal to I1 plus I3. Now, if we write junction rule for point D, what do we have? We have I1 coming in, I3 coming in, and then I2 going out. So we can say I1 plus I3 equals to I2. But you see that these two equations are the same equations. Doesn't give us any new information. This does not give us an independent equation or new information. So we have only one independent equation from the junction rule. In order to get an independent equation, we need to choose a junction that involves at least one new branch whose current is not counted in the previous equations. So when we write this junction rule, we use all these three branches. So if you write this equation for this one, because you're using the same three branches, it doesn't give us any new information. We can only use a new junction if there is a new current branch that is not included in the previous one. All right, does it make sense? So now we have only one junction rule, that is this, okay? I1 plus I3 equal to I2. That's all we get from junction rule. And now we're going to use the loop rule. We have three currents, we need three equations. Now we choose a loop that apply loop rule. Which loop do you choose? There are three loops to choose from. This is one loop, this is another loop, and this is another loop, the large loop outside. All right? And we can traverse each loop either in clockwise or counterclockwise direction. It doesn't really matter. Here, all of them are shown in clockwise direction, but it can be in counterclockwise direction. And what do you think it happens when you traverse a loop in counterclockwise direction as opposed to clockwise direction? Do you know what happens mathematically? Because remember we said that going through different sign for all of them, right? All of them become different sign, opposite sign. It's like multiplying multiplying one equation by a -1. So that doesn't matter. You can cancel that. So the direction doesn't matter. So we choose this one. Let's start with this one. For this loop, we can also choose the starting point. The starting point doesn't matter. For example, if you start here, go around, or start here, go around, or start here, go around, doesn't really matter, because it just changes the order of the term in the equation. Changing the starting point doesn't change the equation. It only changes the order in which each term appears in the equation, which is, because summation is commutative, it doesn't really matter. We can choose point A as the starting point and count the potential differences as we traverse the circuit in clockwise direction. So we're starting from here, we're going through this loop this way, okay? So we also use the sign conventions that we learned. All right, we go from point A to point B, passing battery 1, and we call it B1, from positive side to the negative side. So we said from positive to negative, what is the potential difference? Becomes negative E1, right? So delta V of the battery becomes negative E1, which is negative 18 volts. E1 is 18 volts, right? So this is going from A to B, we get this much potential difference. And then this means that point B is 18 volts lower in potential than point A, okay? So we get the change in potential of 18 volts, negative 18 volts. Then we go from B to D, from here to here. And by doing so, we are moving in the direction of the current I3. All right. So we have delta V3, we call it, delta V from here to here, passing through R3, becomes a negative R3 I3, because we're going in the direction of current. Remember, if the current is going this way, it means that current goes in the direction of lowering potential, lower potential. Therefore, when we go from up to bottom, we lower the potential by this much. So that is negative 12 ohm, because R3 is 12 ohm, times I3 that we don't know what it is. This means that point D is in the lower potential because the current goes from higher to lower potential. Now we go from D to R1 back to A, through R1 back to A, we go this way. Against the current I1, because when you go this way, current is down, so we go against the current. So we have delta V1, we call it, is plus R1 I1. And R1 is 4 ohm here. So we write 4 ohm times I1. All right, so we went from A to B to D back to A. We got 3 potential differences. These are the 3 potential differences. And the loop is complete. So the loop rule says that these 3 potential differences should add up to 0. So we put them equal to 0. Sum of them equal to 0. Therefore, negative 18 volts for the first one, and negative 12 I3 for the second one, and 4 I1 equal to 0. Now we want to simplify a little bit. We can divide this equation by the unit ohm, and everything will be in amps, because this is volt. This is ohm times amps, which is volt, and this is also ohm times amps, which is volt. So everything is in volts, but we can divide by ohm, so everything is in amps, and then we don't write the units. So if we do that, we get negative 18 minus 12 I3 plus 4 I1 equal to 0. Okay? Any questions? So we applied the loop rule to this loop, and we started from A and went clockwise direction, and we added all potentials and set it equal to 0 and simplified so far. So we have 2 equations so far, but we have 3 unknowns. We need 1 more equation. So let's put that here. Now we take this one, applying loop rule for the loop on the right side. We have, again, you see from B, if you go, we get positive E2 and positive R2 I2, and again against I3 we get a positive R3 I3, right? See the positive here, against positive, against positive. So 3 positive values equal to 0. Of course, you see, that means that one of these should be, at least one of these should be negative. All right. And then we put the values. E2 is 12 volts, and R2 is 6 ohm. We put that in here, and R3 is 12 ohm. So we get this equation. Now we have 3 equations and 3 unknowns. So far, so good. Any questions? All right. What if we choose the bigger loop here? If we choose the bigger loop, the larger outer loop doesn't include any new branches. Because you see, we have 3 branches, we already went through all 3. And now if we take the larger loop, it doesn't include any new branches, but let's see what we get if you write the loop rule for that one. Using loop rule for that, starting from A, what do we get? Go from here to here, get 18, sorry, negative 18. Then we get plus 12, and then we get plus R2I2 because we're going against the current. And then here nothing, and then going against the current again, plus R1I1 equal to 0. So negative E1 plus E2 plus R2I2 plus R1I1 equal to 0. So it becomes this equation if you put the numbers in. And then this equation is what you get when you add the 2 previous equations. You see, if you add this with this, what you get negative 18 plus 12. This 12I3 and negative 12I3 cancel. You get 4I1 and 6I2, right? So if you like write loop rule for this outer branch, it is like adding or subtracting the 2 that you already have. So it is not an independent equation. All right. So we have a total of 3 equations for 3 unknowns, which we can solve and get the currents. Any questions so far? All right. Let's put these equations here. And now we want to solve 3 equations, 3 unknowns. You see, this equation is relating I1 and I3. This equation relates I2 and I3. And this one has I1, I2, and I3 in them, all 3 of them. So you see that if I can find I1 in terms of I3 here, and here I2 in terms of I3, and then put them in the first one, then I have only one equation for I3, and then I can solve for I3. So let's first solve for I1 in terms of I3 from this equation. If we divide this equation by 4 and move these 2 over, we get I1 equal to 3I3 plus 4.5, right? So solving this equation for I1. Okay, moving these 2 over become positive, and then divide by 4. We get this. And here, we can also move these 2 over and divide by 6. These are all divisible by 6. You get negative 2I3 minus 2. And now we put these in this equation. So I1 is 3I3 plus 4 in this equation. This is I1, 3I3 plus 4.5, plus I3, which is this one, equal to I2, which is this. Negative 2I3 minus I2, right? So now we see that we have only one I3 in this equation. Now we can solve for I3. If we bring this negative 2I3 over and move this 4.5 over, we get 6I3, right? 2 and 1 and 3, 6I3, and then this goes over, becomes negative 4.5, negative 2 becomes negative 6.5. If you divide by 6 and then you becomes negative 6.5 divided by 6, you can multiply both numerator and denominator by 2, you get negative 13 over 12 amps. This A is amps, is the unit. So I3 is negative 13/12 of an amp. All right. So it is negative, means that the direction that we chose was wrong. I3 is in fact upward. All right. But it's okay. We wrote all the equations in according to this direction, and then it comes up as negative. It's fine. And then once we have I3, we can find I1. I1 is 3I3 plus 4.5. So 3 times negative 13 over 12 plus 4.5. And that becomes negative 13 over 4. Plus, you can also write this as 18 over 4. Becomes this way, and then becomes 5 over 4 amps. So I1 is 5 over 4 amps, and it is positive, means that the direction that we chose was correct. So I1 is 5 over 4 amps, which is 1.25 amps. And I2, according to this, becomes negative 2 times negative 13 over 12 minus 2, which becomes 13 over 6 minus 12 over 6, becomes 1/6 of an amp. So I2 is, the direction of I2 is correct because it is positive. All right? So these are the solutions. Any questions? All right. So solution is pretty straightforward. It's just some algebra and math that you know from before. All right, so these are the values. Now the circuit is solved. We have all the currents, and we can just multiply each current by the voltage and find the multiply each current by resistance, and we find the voltage or potential across each resistor. So once you find all the currents, the circuit is solved. All right, now we want to look at what happens to the energy. Remember, we said that conservation of energy should hold. Now power in each element. Powers of batteries 1 and 2 are, power of battery 1 is I1, because the current going through this battery is I1 times E1. So that is 5 over 4 times 18. That is 22.5 watts. Is that okay? Power of 2 is I2 times E2, which is 1/6 times 12. I2 is 1/6 because the current going through the battery is 1/6, and multiply by the EMF of the battery, 12. So it becomes 2 watts. And then power dissipated in resistors are, power in R1 is I1 squared R1. I1 was 5 over 4 squared times R1, which is 4, becomes 6.25. It's 25 divided by 4, right? And then power in R2, I2 squared R2 becomes 1/6 squared times 6, becomes 1/6 of a watt. And power in R3 becomes I3 squared R3, becomes 13 over 12 squared. So it didn't include the negative because it squares anyway, times 12. So that becomes 13 squared divided by 12. It becomes 169 divided by 12 watt. And if you calculate all of these, it becomes 20.5. Sum of all these become 20.5. But here was 22.5, and this was 2. What's going on? You see the total power of batteries doesn't seem to match with the total power of the resistors. Can anybody know what's wrong? Does anybody see what is wrong? So it seems that the power balance is not right. But we will see that it is, in fact. Why is that? You see this current I2 goes into the positive side of the battery. This I1 going out of the positive. So this battery E1 is providing energy to the circuit or providing power to the circuit, but this E2 is taking power, means it's getting charged, right? So the current in battery 2 is into the positive terminal and out of the negative terminal. This means that it is being charged and therefore takes energy from the circuit at the rate of 2 watts. So the flow of energy is as follows. Battery 1 is putting out energy at the rate of 22.5 watts. Battery 2 is taking energy at the rate of 2 watts, and the rest, which is 20.5 watts, is dissipated in resistors. So the conservation of energy is always valid in every circuit. So in this case, this battery is being charged because this one has more voltage, and because of the currents are in a way that there's current going this way, so this battery gets charged. Again, the conservation of energy is there. Okay, any questions? All right. This is another example. In this circuit, we have a battery of 13 volts, and each one of these resistors are identical, 1 ohm, but this one is 2 ohms. So they are not symmetrical. Find the magnitude and direction of the current in each resistor and the equivalent resistance for this whole thing. What is the equivalent resistance? So you see here again, from here to here, we can say that these two are, we cannot say these are in parallel. So we cannot reduce this circuit basically, because none of the resistors are in series or parallel to each other. All right. So what do we do? Again, we guess the direction of the currents. So I can guess that, okay, this is positive side, the current comes this way from A to B, and then it branches into 2. So the current comes down here, another comes down here, but here we don't know whether the current goes from D to C or C to D. We can just guess that. We can say, okay, from C to D probably, because here is more resistance, so it probably goes this way. And then there is current going this way, and then coming back this way. So these are the direction that we can guess. It may not be correct, but let's see. It doesn't matter if you are wrong. So these are the proposition for the direction of the currents, okay? And then there are 6 branches. You see this is one branch. 2, 3, 4, 5, 6. 6 branches. Therefore, there are 6 currents. All right. And we have 3 key currents. You see, if you know this one and this one and this one, then we can know the other ones from junction rule. So we can, to avoid writing down too many equations, we can apply junction rule right away. So if this is I1, this is I2, and this is I3, then we know what this is. This should be I1 plus I3 in this branch. And then this will be I2 minus I3, and this will be I1 plus I2. So we put those values. So now basically we have junction rule applied. All right. So here I1 plus I2 comes and branches into I1 and I2. Here I2 comes, branches into I3, and this one, which is I2 minus I3, and these two come and join here, I1 plus I3, and then this and that join together. I3 cancels here, get I1 plus I2 again. All right. So this is a trick. You may not want to do that. You can call each one of them 6 currents, and then write junction rule. This is what you get at the end, but this way is more clear, and it'll be easier at the end. All right, any questions so far? All right. Now we have this situation. Junction rule is already applied. We have 3 independent currents, so we need 3 loop equations. You can choose any loop you want. For example, it can be this loop, outside loop. It can be this one. It can be this little one. It can be this one. It can be going from E to F, A, B, and then going to C, then D and E. You see, this is another loop. You can go zigzag this way, whichever way you want to go. But it is better to use simpler ones. All right. The first loop we choose is F, A, B, C, E, F. F, A, B, C, E, F, the outside loop. So if you write that down, write the loop rule for that. From F, we go up here, we pass through the battery, we get 13 volts, right? And then we go through this one, we get R times I2, but R is 1, so it becomes I2. So 13 minus I2, and then minus I2 minus 3 times 2, and we are back to where we started. So that's why we write 13 minus I2 minus 2, the R prime, times the current through it, equal to 0. It makes sense? Any questions? Please stop me if you don't get it exactly. All right, so this simplifies to this. You see, we have negative 3 I2 and plus 2 I3 and 13, it goes over, becomes negative, and then multiply all of them by a negative sign, becomes like this. All right, so simplifying this, you get that. And then we can use another, like F, A, B, D, E, F. F, A, B, D, E, F. Coming back to the same point. So in this case, we have 13, and then negative I1 times 1, and negative I1 plus I3, and back to where we started. So 13 negative I1 plus I3 equal to 0. So again, this becomes negative 2 I1 minus I3 equal to negative 13. Again, can multiply by negative sign, becomes like this. All right. Now we need one more because we have three currents. We need 3 equations. So another one, we can take this small loop. So B, C, D, B, this loop. So if you do that, you get I2 times 1, then I3 minus I2 minus I3 plus I1. Minus I2 minus I3 plus I1 equal to 0. All right. And that becomes I1 equal to I2 plus I3. Any questions so far? All right. Now, again, you see that this equation involves all 3 of them. This equation connects I1 and I3. This one connects I2 and I3. So we can solve this one for I2, solve this one for I1, put them in here, and so we get an equation for I3. So this one, solving for I2 becomes 2I3 goes over, and then divide by 3. We get I2 equal to 2/3 I3 plus 13/3. And here becomes negative 1/2 I3 plus 13/2. Negative 1/2 I3 plus 13/2 for I1. And then we can put them in here. So I1 is negative 1/2 I3 plus 13/2 equal to I2, which is 2/3 of I3 plus 13/3 plus I3. Okay. So we put these two equations into the third one, we get this equation. All right. And now we can solve for I3. If we move this over and factor I3, we have I3 times 1 plus 1/2 plus 2/3. And this one comes over, becomes 13.5 minus 13/3. So we get this equation. And then you can make common denominator if you want, or multiply by common denominator. So this is combining these three fractions, and this one is combining these two fractions. 13/6 becomes 3 times 13 minus 2 times 13, so it becomes 13/6. So then we have that, and then we can solve for I3. You see, this happens to be 6 plus 3 plus 4 is also 13. So I3 times 13/6 equal to 13/6. So I3 is equal to 1 in amps. All right. And then if you put that I3 into this one, -1/2 plus 13/2, 13/2 becomes 6.5 minus half becomes 6 amps. So I1 becomes 6 amps, and I2, this is 2/3 plus 13/3 becomes 15/3, becomes 5 amps. So we have all three values. So we get all positive results. That means that our original guess about the current directions were correct. All right. As a practice, you can check for the conservation of energy. You should find that the energy output for this 13 volts. What is the current? I1 plus I2, I1 and I2. So that's 13, right? No, 11. 11 times 13 is the total power output of the battery. And then you see that it will be equal to this total power dissipated in all the batteries. Right? I'm not doing that here. You can do it by yourself. But what is the equivalent resistance? As I said, this wasn't a case where you could just make parallel or series resistors and reduce it to one equivalent. But by finding the total current, which is I1 plus I2, which is 11 amps, and the total voltage, you can find the total resistance here. So our equivalent will be V divided by I total, means I1 plus I2. So 13 volt divided by 6 plus 5. If you divide 13/11 becomes about 1.180. So the whole combination has about this much resistance. Any questions? All right. Now, another part of this chapter is RC circuit. RC circuit is a circuit with a battery and a resistor and a capacitor. That's why it calls RC circuit. So we have first the capacitor is uncharged, and we have this situation. We close, this is a switch. We close it on A, then the battery starts charging the capacitor. When switch S is closed on A at time equal to 0, t equal to 0, the initially uncharged capacitor C starts to charge. At a later time, t, there will be a current I in the circuit in clockwise direction. And the capacitor gets a charge Q with the top plate positive. So some charge goes here, and of course it starts charging. A later time, this has some charge, then we have some current, and we want to see how we can write the charge as a function of time, for example, or the current as a function of time. So we apply Keshov laws, Keshov rule, loop rule for this circuit when it is connected to A. So we say V, then we go through the resistor, we minus IR, and then we go through the capacitor, becomes the potential difference here, but we go from positive to negative, and potential difference is Q over C and negative. So we write V minus IR or RI minus Q over C equal to 0. So this is Keshov loop rule for this circuit. But this current is related to the charge because the charge is because of the current. And as the current flows, the charge increases. And you know that the current becomes rate of change of the Q. Okay, I becomes dQ dt. Therefore, we can replace I by dQ dt. So we get this equation. V minus R dQ dt minus Q. This is a function, an equation between the this function of time. Q is a function of time. R and C and V are all constants. Q is a function of time, and this is the derivative of Q. Have you heard of an equation between a function and its derivatives? Have you heard of it? Anybody?
Differential equation?
Yes, it's a differential equation between for Q and its derivative. And it is a linear equation, linear differential equation, because the powers are all 1. I mean, the power of the derivative is 1, power of Q is 1. So it is a simple first order. Also, it's called first order because the derivative is only one derivative. Doesn't have a double derivative. Just one derivative, each one is power 1. So it's simple first order linear differential equation. All right. And the question is, okay, what is Q as a function of time that satisfies this equation? So how do we find that? I'm sure some of you have already seen differential equation and you know how to solve this equation. Do you know? Anybody knows how to solve this equation of this type? Maybe not. All right. One of the ways we can solve this equation is by separation of variables. You see, there is a function Q like Y, and there is a variable T. No, it is a first order partial, is a first order differential equation. First order linear ordinary differential equation. It's also ordinary differential equation as opposed to partial differential equation. And so we need to separate. One of the ways we can solve this is to separate the variable Q from the variable T. And that then we can integrate. So if we move V and Q over C to the other side, then we have dQ dt, and then we can put dt on this side, all of these on the other side. So dt equals R dQ divided by V minus Q over C. And then now you see that one side is only T, the other side is only Q. This is called separation of the two variables. Of course, Q is dependent variable, T is independent variable, but they are variables. So this way we separated the two variables. To write this in a better way, we divide both sides of this equation by RC. So this R goes away and C that comes here multiplies, this becomes CV, and this becomes just Q. So we can write it this way. dt over RC equal to Q over CV minus Q. And now we can integrate both sides. And 1 over RC is constant, comes out of the integral. We get integral of dt on this side. The other side becomes integral of dq divided by CV minus q, right? And you know how to integrate. Integral of dt becomes just t. Integral of this, you can take the denominator as u, and then you write dq in terms of du, and then you have integral of du over u, then you that becomes ln of absolute value of u, and there's a constant of integration. So with that, du becomes negative dq, right? Therefore, this becomes t over rc on this side equal to negative du over u, and that becomes ln of absolute value of u, right? And with the negative sign, a negative ln of absolute value of u, and then where there is a constant for integration, we should add. All right. So C1 is a constant to be determined using the initial condition. So this C, of course, is a constant as far as this equation goes, but we want this function Q as a function of time to match the initial conditions. So that determines what C1 should be exactly. So let's put this here. And then what is the initial situation? So instead of U also, I put CV minus Q, okay? So T over RC is equal to negative ln of CV minus Q, absolute value, plus C1. What was the initial condition? At T equal to 0, we have Q equal to 0. So we put T equal to 0, and also we put Q equal to 0, see what C1 should be. So 0 equals negative ln of CV plus C1. And of course, CV is positive. We can take away the absolute value. So C1 is ln of CV. So we put it back in the original equation. And also we know that CV is positive and CV minus Q is also positive. So we can take away the absolute values. Substituting C1 equal to ln of CV, we get this. T over RC equals negative ln of CV minus Q plus ln of CV. Okay. And then we can write as this. We move this over and move that one over, or you can multiply by a negative sign, and then ln of A minus ln of B becomes ln of A minus B. All right, so ln of CV minus Q divided by CV. All right, and then CV minus Q divided by CV becomes e to the power of negative T over RC. So we get that. And then we can solve for Q. We multiply by CV, we get CV minus Q equal to CV e to the negative T over RC. And then we solve for Q becomes CV minus CV e to the negative T over RC. And then we can factor the CV, becomes 1 minus e to the negative T over RC. All right. So this is the solution to that differential equation we were talking about. This function of time, Q as a function of time, which is like this, it satisfies that equation with its initial conditions. Let's look at some limiting cases. At T equal to 0, what do we have? if t is equal to 0, what is e to the negative 0? E to the 0. E to the 0 is 1, right? Yes. 1 minus 1 becomes 0, so q becomes 0 as, yes, as we expected. Okay, so we have q equal to 0 as we expected, and we actually put the condition to get the q. So we didn't make a mistake, so it should come out right. At t equal to infinity, what do we get? E to the negative infinity becomes 0. So as t goes to infinity, this q goes to CV. So e to the negative t over RC goes to 0 and q goes to CV. This CV is called final charge, Q final, of the capacitor. At t equal to RC, what happens? If t is equal to RC, we have e to the negative RC over RC, or e to the negative 1. So Q becomes CV, which is final charge, times 1 minus 1 over E. All right? Or becomes, this 1 minus 1 over E becomes 0.632, or 63% of the final charge. All right? So this is how the function works. Starts from 0 at t equal to 0, and then goes up and to Q final. And at this time, it goes to half of Q final. As at RC, it goes to 63% of Q final. And the difference now between this point to this point is QF over E, which is for that 37%, the rest of it, right? But if you look at the current, how does the current change in here? Current is dq dt, right? So you can take derivative of this q with respect to time, you get the current. And the first term is CV times 1. The derivative of that is 0. And then we have negative CV e to the negative t over RC. Then you see here, negative CV e to the negative t over RC, if you take derivative with respect to t, becomes itself times the derivative of the exponent with respect to t, which is negative 1 over RC. So negatives cancel out, and CV over RC becomes this V over R. V over R is the initial current when the capacitor was uncharged. We had this only V and this R, the initial current will be V over R. We call it I naught. And then the rest of it becomes e to the negative t over RC. And I naught is V over R. So the current starts from I naught and goes exponentially to 0. And of course, at this point, at this time here, you get to half of the initial current. At time equal to RC, you get I naught over E. All right, means 37% of initial value. All right. Now, this T equal to RC is called the time constant of the RC circuit and is denoted by the Greek letter tau. And so we say tau equals to RC. And in terms of this tau, we can write this in terms of tau. So Q as a function of time becomes final charge times 1 minus e to the negative t over tau. And the current becomes initial current times e to the negative t over tau. This time constant is R times C. For example, if you have 1,000 ohm and capacitor of 1 microfarad, then T becomes 1 millisecond. So for ordinary amount of resistors and capacitors, this charges very fast. And then look at when t equals to 5 tau, is if time is equal to 5 time constant. T equals to 5 time constant, we have this Q equal to final charge times 1 minus e to the negative 5 tau over 5, which is e to the negative 5 here, becomes a very small number. So becomes 0.993 QF. Means that in 5 time constants, the charge is the capacitor is almost charged. After t equal to 5 tau, the capacitor is more than 99% charged. All right. Any questions? All right. So we have a few minutes. I'm going to talk about discharging capacitor. I go a little bit faster here because we don't have much time. So now that the capacitor is charged, and then we can disconnect the switch from A and connect it to B. Then what happens? Then the charge flows through the circuit and the capacitor discharges. This is called discharging capacitor. When the capacitor is charged, if the switch S is now closed on B at time t equal to 0, the capacitor starts to discharge. At a later time t, there will be a current I in the direction, in counterclockwise direction, and the capacitor has a charge Q with top plate positive. Applying Keshov loop rule in clockwise direction for the loop with no battery, you see this loop now. This one is connected to B. If you go this way, you get IR, and then here from positive to negative, negative Q over C, RI negative Q over C equal to 0. But now the current and Q are also related. And in this case, if the current is in this direction, which we consider positive, then that reduces Q. So it means that the current is negative of rate of change of Q. So I becomes negative dQ dt. And then if you put that in here, you give negative R dQ dt minus Q over C equal to 0. And then we can solve this for Q as a function of time. Again, we move this one over like that. And then now we put dt here and Q here. And we put negative R also, divide by negative R as well. So dQ over Q equals to negative dt over RC. So if you integrate, this side becomes negative T over RC. This side becomes integral dQ over Q, which is ln of Q plus a constant, right? And because Q is constant, Q is positive, we don't need to put absolute value. So what is C2? C2 is again determined by initial condition, which is when T equal to 0, we have Q equal to Q naught. So we put T equal to 0 and put Q equal to Q naught, and then we find C2. So 0 equal to ln of Q naught plus C2. So C2 should be negative ln of Q naught. And then we put it back in the equation here. And so we have that. And then we can write it as ln of Q over Q naught. And then we write Q over Q naught equal to e to the power negative T over RC. And then we multiply by Q naught, we get this. So this is a discharging capacitor. And if you take derivative, you can get the, again, negative 1 over RC comes here. And of course, with the negative sign in here, the negative goes away. and Q naught over RC becomes I1 because I naught, initial value of the current, because Q naught over C becomes initial potential across the capacitor, divided by R becomes initial current. So this I naught is Q naught over RC. All right. And then if you look at the graph, it will be like that. At the one time constant, again, the charge drops to 1 over E of its initial value, and the current also drops to 1 over E of its initial value. All right. Any questions? All right. I stop here. Thank you for your attention. If there is any question, I'll be here to answer.